So we're back, and in this video we're going to continue talking about hybridization theory, and this is where we left off. And we said in order for carbon to really get four bonds that it can share with other atoms, because this is where the formal charge is 0, that we need 4 available electrons to share. So that means they need to be single. So we talked about this process that organic chemists have basically made up, and we said the only way that this could work is if we promote. We promote an electron from one orbital to the next. And this will allow us to have 4 single valence electrons in the outside shell that can participate in bonding, giving carbon 4 bonds to other atoms. Well, because we are involving a P or an S, and because we're involving all 3 of the P's, we call this an sp3 hybrid. So the shape of that orbital begins to change. It is that traditional lobe of a P, or the top half of that figure 8, and the S also comes into play. So it affects the shape just a little bit, and we get an offset or a balance according to this subshell. So the issue, though, is that this just doesn't happen with carbon, and it also doesn't happen this way every single time. So here I'm going to give you another example. You know, we drew the structure of carbon dioxide, okay, and this is what we ended up with. We had oxygens with 2 pairs of electrons on each. Those oxygens have 2 bonds to give it a formal charge of 0, and the carbon in the center has 4 bonds, which gives that a formal charge of 0. So this is the accepted structure of CO2. However, what we have here is a double bond. It's not a single bond. And if I look, it seems, though, that carbon is only attached to 2 other atoms. I know there's 4 bonds in total, but it only goes to 2 other atoms. So here we have a different type of scenario. The scenario is there's not 4 single bonds going to 4 atoms. That is an sp3 hybrid. Here we have a different scenario. We have a different case. All right, so I'm going to start with the electron configuration of carbon again, just so I can walk you through that one more time. And then down below, we can draw the representation of all of the principles that we've learned about. So I'm going to start filling these in. Here are the degenerate P's, and we have 1 and we have 2. So in this case, we have a double bond, not a single bond. But the only way that this is going to work, because there's still 4 bonds in total, right? The only way that this is going to work is if we did what we did last time. We have to kind of make believe that this electron sees the empty bedroom of the house, decides that it wants to move and not share its bedroom anymore, and then go to the empty room here, maybe the attic, or maybe the basement, depending on how good or bad they were. Okay, so this sets up the play that 4 available electrons are there again to participate in 4 bonds. But this time it's a different type of bond. It's a double bond. So what exactly happens here? Well, if we take a look at what goes on, it seems that this bonding characteristic is a little bit different. Well, how is that the case? So in order for me to explain this maybe a little bit better, let's do another example that might be a little bit easier to see, that's more true organic. And we'll kind of wrap all 2 of these together in the same description. So let's say that we had a organic molecule that looked like this. No oxygens, just carbons, just hydrogens like we did before when we talked about sp3 hybridization. And we're only focused right now on 1 double bond, not 2 of them as from up above. So the same theory kind of goes on here, folks. There's no difference. This is just maybe a little bit truer to the world of organic. So this carbon, this particular carbon, and this particular carbon both show that electron configuration, just like this carbon does. The electron configuration does not change on anything. So if I look at the carbon example down below, there's only 1 double bond that we have to worry about. And there's 2 other bonds that go off from that carbon. And those 2 bonds go to 2 different atoms. okay? The same kind of scenario happens up here at the top. We have a carbon with a double bond that goes to an O, and then there's two other bonds that are associated to that carbon at the same time. All right, well, down here below, with the structure of what we are going to call ethene, this carbon doesn't need to be fully sp3 hybridized. sp3 hybridization gives rise to 4 separate bonds, to 4 different things, or the 4 same atoms. There's not 4 atoms attached to this carbon. There's a hydrogen, and a carbon. There's 3 in the example down below. So, actually, what happens here is that this carbon only needs to utilize the s and 2 of the p orbitals. So when it does that, this becomes an sp2 hybrid. And that s will give 1 bond, and the 2 p's will give 2 other bonds to 3 different things. And that's what we have over here to the left-hand side. We have a hydrogen and a carbon. 3 atoms, that's the way I want you to think about it. 3 atoms attached to that carbon. Therefore, 2 plus 1 is 3. 3 represents sp2. If I look at the sp3, 3 plus 1 more from the s gives me 4. That carbon has a total of 4 bonds to 4 different or the same atoms. Okay, that's the narrative that I want you to start paying attention to. So this carbon's 3 atoms attached. One of them's a double bond, but 3 atoms are attached. Therefore, this is an sp2. All right, well, the first sp2 is going to happen here to the hydrogen. The second sp2 will happen here to that hydrogen. And the third sp2 is going to happen here to that particular carbon. Now, what we have left over is something that wasn't used. And this thing that's not used is a sp2. And that, is another p orbital. And it did not get affected, right? This hybridization only allowed s and 2 p's to come together. So what we have here is a p orbit, maybe pz, that has this figure 8 shape, and there's an electron that circles in that figure 8 shape around that carbon. All right, well, the story happens the other way on the other side as well. This particular carbon is also sp2 hybridized. There's a double bond that's present. So this particular carbon, I'm going to change colors here, will have an sp2, there's one of them, to the hydrogen. It will have an sp2, there's the second one, to another hydrogen. It will also have this one as well that it shares, that is also an sp2 to the other carbon. There's your third, therefore sp2 has now been fulfilled. And this carbon did not use its last p orbit either. So it has a maybe pz that this one electron floats around in that did not get used and did not get affected. Now what happens is that the left-hand carbon and the right-hand carbon come together and say, I've got this loner, you've got this loner. So why don't we overlap our p orbits? And we will share the same space with our p orbits. And when that begins to happen, they begin to merge in a way, and they begin to share the same space. But did you see what word that I used? I used the word share. They're sharing the same space. So this is the formation of the double bond that we draw in the Lewis dot structure. That is how double bonds are formed. So the double bonds are formed by a single bond first, and then the overlap of the p orbitals will give us that second line that we draw in these Lewis dot structures every single time. Okay, so all of this is driven by sp2 hybridization. It's a little bit different than sp3. sp3 used them all. Therefore, there wasn't a free electron that was available to do the overlap. Those were attached to 4 atoms, whether they're the same or different, but those 4 atoms took up each one of the sp3s. In this case, there's 3 atoms, not 4. Therefore, one of these will not be used, and that extra that's not used will begin to overlap, and it will begin to create a double bond, which is extra glue that holds these 2 carbons together. It holds them a little bit closer, it holds them and nestles them a little bit tighter, but it's also more reactive, because this is an area now that has 4 electrons that are present and not 2. So if I'm looking at charges throughout the structures, that is going to be a problem area possibly, because there is more of a condensed area of electrons in that location. All right, so that is an sp2. Here is an example of sp2 hybridization that you might see in your textbook if you begin to look at it. Notice they did the same thing that I did. They promoted the electron to the p orbital just like you would with sp3, but they're only going to use 3 of these because there's only 3 atoms that are attached to that carbon, not bonds, but atoms. This gives us an availability into that p orbital, maybe a px, maybe a py, maybe a pz, but it's a p that's freed up. And this carbon has a free p, that one has a free p. They overlap those p electrons or pi electrons to create, or a p electron to create a pi bond, and that's what we call a double bond. Again, down here below, here's your stick formula. Here's your ball and stick formula, here's your space filling model, and then here's your electrostatic potential map. But over here, finally, 3 sp2 hybrids, and then this one does not hybridize because there's only 3 atoms that are attached to that carbon. Again, I keep saying it, atoms, not bonds. Here's another example of sp2. This sp2 is just showing you a little bit of geometry. We will wrap this geometry up all in one kind of lecture video. I think it's better to view it at the same time than scatterbouts. But this is just another example of sp2, maybe looking from the top. So in this last case, this would have been to hydrogen. This would have been to hydrogen. This one possibly to that carbon that was also there. And then this purple orbital, this is a lobe that's pointing up and a lobe that's pointing down, but this is the orbital that begins to create that double bond right there kind of in the center. Here's the side view of it. Again, this would have been to the hydrogen, this would have been to the hydrogen, this one would have went to that carbon, and then this purple orb that goes up and down, this is your P shape, and this begins the overlap with the neighboring atom to give us that extra bond that we call a double bond. So here is the depiction of it together in one whole result. Maybe they draw it a little bit better than I did on the slide. If so, that's okay. No one said that I was an artist. And we have a carbon to the left and a carbon to the right. Here is the original bond that connects the two of them. So that would be the original sp2 bond that's there. And then here's a lobe and there's a lobe. Here's a lobe and there's a lobe. And notice they just kind of smudge those lobes together. When they do that, this is the presence of a double bond, and this is how they get created. Notice on the screen at the same time, they are starting to label these differently. No one wants to write down the word single bond, and no one wants to write down the word double bond every single time that we have to use them. So if you notice, what happens here is that we have a shortcut method. And this squiggly symbol, that is the sigma So that sigma represents a single bond, and the double bond is going to be represented with a pi formula, or the Greek letter. So sigma and pi is a shorthanded way that we can write down the word single and we can write down the word double whenever we talk about bond characteristics. So that will always be in play. We will kind of bounce back and forth between calling it sigmas and pi's and singles and doubles, but that is what those symbols represent. Now, this is not the only choice. Last video we talked about all singles, 4 bonds in total to 4 atoms. This time we talked about sp2 hybridization, which was an atom that's attached to 3 others, and a double bond gets formed. So there's one more major example that we want to talk about before we leave hybridization theory, and that's what's going to be presented in the next video. So stay tuned. After a double bond, we do have things that are called triple bonds, and you'll learn about those next.